Welcome to this lecture on 5G mobile communications and connectivity, presented by Dr. Microlearning. Over the next few minutes, we'll walk through the core ideas that make 5G different from previous generations, from performance targets and network architecture to real-world use cases, so you'll finish with a clear view of why 5G matters and where it's headed. This slide lays out the official 5G blueprint. Think ultra-high throughput, millisecond latencies, massive device densities, and support for high-speed mobility, all delivered with big gains in energy and spectrum efficiency. The diagram highlights how these goals combine to enable new services. So keep in mind, 5G is really about balancing capacity, responsiveness, and scale. 5G rests on three service pillars: enhanced mobile broadband for immersive, high-speed experiences, ultra-reliable low-latency communications for mission-critical control, and massive Maschine-Type communications for denser, low-power sensing. The graphic shows how network slicing pulls these divergent needs together into a unified framework that can deliver tailored connectivity for each use case. To meet diverse latency and coverage needs, 5G introduces a flexible radio frame with scalable sub-carrier spacing, mini slots for instant transmission, and dynamic TTI adaptation. The visuals illustrate how changing symbol duration and slot structure optimizes performance across environments, enabling both wide area coverage and ultra-low latency for time-sensitive applications. Millimeter wave propagation brings capacity, but also signal loss. So 5G uses advanced beamforming and large antenna arrays to turn that loss into directional, higher capacity links. The flowchart shows digital pre-coding, dynamic beam steering, and spatial multiplexing, working together to deliver multi-1 gigabit throughput and increase spectral efficiency. Despite harsher propagation conditions, the 5G core is built around virtualization and modular services, with a service-based architecture, separation of control and user planes, and SDN, NFV orchestration. The diagram highlights how isolated network slices run on shared physical infrastructure, enabling flexible, secure logical networks tailored to eMBB, URLLC, or MMTC needs without duplicating hardware. Different frequency bands trade off coverage, capacity, and device complexity. Lower bands give wide coverage and deep indoor penetration. Mid bands balance coverage and high data rates. And mmWave delivers extreme capacity but needs line of sight and densification. The table reinforces why dual-frequency handsets and mixed deployments are essential for seamless performance. Operators often start with non-standalone 5G that anchors to existing 4G cores for faster rollout, then migrate through hybrid and dual connectivity stages toward a standalone 5G core. The migration diagram explains operator incentives, phased upgrades, and how moving to a native 5GC unlocks advanced services like network slicing and full URLLC support. Densification and CapEx optimization are key to unlocking dense 5G performance. Indoor picocells for localized capacity, street-level mmWave repeaters to fill outdoor gaps, and shared infrastructure to spread costs. The slide shows how combining these strategies lowers total cost of ownership while supporting venues, enterprises, and smart city applications. Last-mile connectivity is being disrupted by beam-steered CPE that can deliver gigabit speeds wirelessly, dramatically reducing the cost and complexity of fiber drop deployments. The comparison highlights lower last-mile CapEx and faster rollouts, plus market effects like increased competition and pressure on traditional cable operators to innovate. On-premise, non-public networks, deterministic TSN integration, and Edge MEC create closed-loop automation with sub-halp 10 millisecond control. The diagram connects dedicated spectrum and local processing to real-time robotics, AGVs, and AR maintenance, showing how industrial sites can achieve reliable, low-latency automation without relying on public networks. Sidelink Mode 4 enables direct vehicle-to-vehicle communication for cooperative awareness and platooning, while vehicle-to-infrastructure links support traffic management, hazard warnings, and dynamic routing. The dual illustrations emphasize lower latency, scheduled sidelink communication, and how these capabilities combine to enhance road safety and traffic efficiency. Sustainability is a core 5G design goal, with improvements in bits per joule, sleep state micro GTX for idle efficiency, and renewable-powered edge sites to reduce carbon footprint. The slide underscores that energy optimization and green power at edge locations help align 5G expansion with operator carbon-neutral pledges and long-term environmental targets. 5G security upgrades aim to mitigate legacy threats by combining strong encryption, mutual authentication, privacy protections, like SUSI, and logical isolation through network slicing. The schematic shows how these measures protect signaling and user data, reduce SS7 area vulnerabilities, and make it harder for fake base station attacks to succeed. Looking beyond 5G, the evolution towards 6G involves AI-native networks, sub-centimeter wave operation, and reconfigurable intelligent surfaces as stepping stones. The roadmap points toward a 6G vision around 2030 that blends joint communication and sensing with terahertz systems, setting the stage for even tighter integration of wireless connectivity and the physical world.